Hello. All right, let's get started. Today, the only thing I want to focus in on is the calculus notation that we're going to use to describe the antiderivative and specifically how the antiderivative relates to areas underneath the curve. It's the only concept that we need to focus in on. So first thing is I'm going to start with a problem that we should be able to figure out. F of x is equal to, we have the absolute value of x, and we're going to look at the interval from -2 to 2. And what we want to think about is, given this function, what is the area underneath this curve? So specifically when it's less than this curve but greater than the x-axis. So what is the space in between here and in between there? Well, we can figure that out geometrically. Area of a triangle is 1/2 base times height, right? So if your base has length 2, your height has length 2, base times height is 4, 1/2 of that is 2. You can also see that because here's a square. Here's a 2 by 2 square. 2 by 2 square. Yes.
Are you sharing your screen right now? Because we can't see anything.
Good point. Thank you.
No problem.
All right, let's see here. All right, now you can. Thank you for chiming in. All right, so we're looking at absolute value of x from the space -2 to 2, and we want to think about the area underneath these two curves between the x-axis and there. So you get these two triangles, and we see that this is a 2 by 2 square, so that's got an area of 4. This triangle is half of that, so this triangle has an area of 2. This triangle over here also has an area of 2. So the total combined area underneath this curve is 4, because you add the two together. So that's the area underneath the absolute value of x within this interval. So how do we write this mathematically? And so we're going to use this. I'm going to switch you over to the screen. This is new notation. So this is integral notation. And what we're doing, these are our values that we're integrating over. And then this is the function. And so the answer to that is it's equal to 4. So this is literally saying, what is the signed area underneath the absolute value of x function from the interval -2 to 2? That's what this notation states. And it always comes with this dx. We always put that at the end of it. And in this case, the answer is equal to 4. We just need to figure out what the area is, the signed area underneath that curve. And then we can get that. Let's take a look at, I'm going to write one out now using this notation, and then let's go interpret that inside Desmos. I'm picking easy functions too, ones that we can calculate. 0 to 3. All right, so this one is saying calculate the signed area underneath the graph of x on the interval 0 to 3. So what's the signed area in that space? So let's bounce back to Desmos and see what that looks like, and then calculate it just using geometry. Hide that. So it's function x, and it's specifically from 0 to 3. And we want to find the area for here. So 1/2 base times height. Your base is length 3, your height is length 3. 3 times 3 is 9. So half of 9, 4.5. So the answer to that integral problem is it's equal to 4.5. So it all comes down to, it really is just about geometry, about being able to add up these areas. There are some small caveats that these two problems avoided. Let's work with this x again. Let's change it though a little bit. Let's change it so that I don't avoid something I've been specifically making not a part of these problems. So let's say, what if I change this from -2 to 3 of x dx? What does that equal? -2 to 3. Let's go back to the graph. So now we're going to go from -2 to +3. And it's just a signed area, right? I keep saying this signed area. What does that mean? Well, from 0 to 3, we saw that this had an area of +4.5. Now, this over here, this is below the x-axis. So what is the area that we're actually measuring? We're measuring this area right here from the function up to the x-axis. And because it's below the x-axis, not because it's to the left of the y-axis, but because it's below the x-axis, we consider this space negative space. And so whatever this area is, it's negative. And so when we want to calculate the combined area from -2 to 3, we're going to actually subtract this value from here, from 4.5. So now this triangle right here, this has got a base of 2 and a height of 2. So it's 4. So 1/2 times 4 is 2. Saying that right? Yeah. So this has got an area of -2. So the integral then from -2 to 3 is 4.5 minus 2, which is 2.5. So the combined signed area is 2.5, because this negative space needs to get subtracted from here, and you're only left with 2.5 space after that. Go back to Word and put that in there. All right, so this was equal to 4.5 minus 2, or plus -2, which is equal to 2.5. So the 0 to 3 we saw, it's the -2 to 0, which was this -2. So let me explicitly write that out, in case anyone, this helps. -2 to 0 of x dx was equal to -2. is equal to -2 because the space you were measuring was below the x-axis. And so that's what makes it negative. Let's try some other ones. All right, let's do, so these are all ones that we've been able to just calculate geometrically because we can draw them. What about a space that we can't do geometrically? What if we wanted to, this was one that we were looking at last class, but we didn't write it out like this. What if we want to calculate 0 to 2, if you just do 0 to 1, x squared dx. Right, so now with this new notation, this is saying, given this function x squared, what is the area underneath the interval from 0 to 1? Let's visually see that. So we want to calculate that area. There's no geometry tricks that we can do to figure that out. We could draw a lot of rectangles underneath here and add those all up and try and be as accurate as possible. The more rectangles we drew and fit underneath here, the closer and closer we would get to getting to that value. And if we did this an infinite amount of times, if we did draw an infinite amount of rectangles underneath here, we would get the correct value, and it would end up coming out to being the integral underneath this function. And the integral is just the antiderivative as well. So what we're going to do is to figure out what the signed area is underneath here. One thing we know, it's positive because the space is all above the x-axis. Positive value. We could also make a guess at what it is. It's got to be less than 1. That's one thing I know. Why? Because it's inside a 1 by 1 square. That square has an area of 1. So this has definitely got an area less than 1. This looks like it has an area less than 1/2, right? Because if I cut this in half and threw that away, there'd still be a little bit of extra space here that I could throw away. So this has got to be a number between, the area of this space has got to be a number between 0 and 1/2. All right, so let's try and solve that. Word. All right, so how do we write that out? Some of this is new notation, but the first thing we're going to do is we're going to calculate the antiderivative of x squared dx. That's what this notation is telling us to do. Calculate the antiderivative. Remember, the antiderivative is the function that this came from. Is there a function that when you take its derivative, you get x squared out? Yeah. It would have to be right in terms of some x to the third. And right when you take the derivative of x to the third, you bring that 3 out in front, and then you subtract 1 from the 3, so it becomes a 2. But this x squared doesn't have anything in front, which means it had to have a constant in front of it that canceled away. So when you take the derivative of 1/3 x cubed, 3 times 1/3 is 1, 3 minus 1 is 2, and that's your x squared. When we did antiderivatives last class, we put a plus c. And we were doing plus c's. In this type of problem, we don't need to do any type of plus c's. And the reason is because of these index values right here. These index values give us a definitive space that we're working within. And so we're going to get definite answers. And so there won't ever be a plus C. So this symbol tells us to take the antiderivative of x squared, and we take it, and we get this right here. We now go ahead and let's see if I can get this notation right in Word. Let me see if I can just do it on my own. This out 1 second. I'll use this. All right. Yep, there we go. 1. So this is just notation, but you'll see it a lot with this stuff. So it's important that you understand how to read this. Okay, so this is the problem. This is saying find the signed area underneath x squared between the interval from 0 to 1. The process of actually being able to do that without using geometry is that you take the antiderivative of this function and you write it out, and then you put this straight line to the right of it. This squiggly line turns into this straight line, okay? And then those two numbers just go ahead and appear right there at the top and the bottom of it. This new notation has a algebraic meaning, and what that's telling us to do is to plug those numbers in. So the first number we plug in is 1, because that's at the top of that line. So 1/3 times 1 to the 3rd power. And then the next operation is to subtract whatever the bottom number put into 1/3 x cubed is. But you need to subtract it. So 1/3 minus 1/3 0 cubed. So that's equal to 1/3 minus 0, which is equal to 1/3. The area, the signed area underneath x squared from 0 to 1 is 1/3. That's what this all means. And this is that process of being able to do that without geometry. This is the calculus part. We don't explain or prove why this is true. We skip that in Calc A. But this is a true, very true thing involving limits and adding up an infinite amount of rectangles underneath a space, and we can show that it is the antiderivative of that function, and then we can measure it just by doing this. So that's how we do that one. Let's try another problem. Then it just becomes repetitive. All right. I think if I can think of any good ones here. Either the X. That's a good one. All right, so yeah, 1, 0, stick from 0 to 1. This time we'll do e to the 2x dx. Right, so we want to find the signed area underneath the curve e to the 2x dx. So the first thing we have to do is find the antiderivative of e to the 2x. Think about that. That's a... Wait a minute. I'm trying to think here. Is this one that we can do? Yeah, this is one we can do. Yeah, okay. So think about e to the x in general. When you take its derivative, it basically remains the same, except if the numerator was a little bit different, then you have to take the derivative of that. So there's a 2x there. That's different. So the derivative of 2x is 2. So we have to say to ourselves, well, it's definitely going to be something e to the 2x. Because when you take the derivative of e to the 2x, you keep it. It doesn't change. It's going to be itself. But then times the derivative of the exponent. So I'd have to account for the fact that there's no 2 out in front. So there had to be a 1/2 there. And that's the antiderivative, because take the derivative of that. E to the derivative of e to the 2x is e to the 2x times 2. And the 2 times the 1/2 cancels out, and you're just left with now e to the 2x. So we're going to now update the notation. And we're going to run this from 1 to 0. Yeah, it doesn't mean perfect. That's all right. All right, so we plug the 1 in. So 1/2 e to the 2 times 1, so e squared, right? And then minus, you plug the 0 in, 1/2 e to the 0 power, 2 times 0 is 0. And that's equal to 1/2 e squared. E to the 0 is 1, so minus 1/2. Factor out that 1/2, make it look real nice. E squared minus 1. So that's the area underneath that curve. Okay. Let's try this for a trig problem. Let's set one up where we know the answer ahead of time. Let's take a look at a trig problem. Let's do this. This will hopefully help with the signed area piece, which is something of a concern of mine that you guys understand. So let's just consider sine of x real quick, and only consider it from 0 to 2 pi. Right? So let's just consider that space right there. The area underneath this hump right here is definitely the same area here, right? Except one is, this will be considered positive area because it's above the x-axis, and this will be considered negative area because it's below the x-axis. But they're definitely the same amount of space. I think we can all agree on that. So if this signed area thing is true, that like this taking the antiderivative and all that stuff and then plugging these things in, if that stuff all works, then when I take the integral of sine of x from 0 to 2 pi, should be equal to 0. Think about that. The integral from 0 to 2 pi, this is 2 pi all the way over here, of this function should be 0, because that's what the integral gives us. It gives us the signed area under the curve. And we know that this signed area right here is equal to this signed area right here, except they're positive and negative. So they're going to cancel each other exactly out. So let's try that. Let's mathematically see that happen using the notation that we're learning. All right, so we're going to do the integral from 0 to 2 pi sine of x dx. So again, we don't have a geometric solution. Like if this is a type of problem, you should definitely consider maybe there's a geometric way of solving it, because geometry is pretty easy and a good way of coming up with those numbers. But this is one where that's not going to be the case. You could do the argument that you could go ahead and say, well, I know about signed areas and that this is going to cancel each other out, and therefore the area will be 0. That's a good argument to be made as well. But here, let's see it actually come out to this. So we're going to take the antiderivative of sine of x. What function did this function come from? Well, it definitely came from cosine, right? But if it came from cosine of x, the derivative of cosine becomes a negative, right? It changes signs. But this sign here is positive, so cosine had to be negative. Had to be negative. Because when you take the derivative of negative cosine, you then get positive sine. So that's the antiderivative. We're going to put that notation, that little structure on here. And go up. And that's 2 pi. Down. Yeah. I don't want that. So now we're going to calculate that from 0 to 2 pi. So we take negative cosine of 2 pi. And we do minus, you always got to put that minus. Now, what is it again? It's negative cosine of 0. You got to keep careful watch of all the different signs. This minus comes from the process alone. These minuses are because the problem itself has a minus in it. So now that's equal to cosine of 2 pi. 2 pi, you're at 0. And you're measuring the horizontal distance to the vertical axis. So that cosine of 0 or cosine of 2 pi is 1. So that means negative 1 minus cosine of 0. So minus a negative cosine of 0 is 1. That's a negative 1 then. Hey, lots of negatives here. Negative 1 and a plus 1 is equal to 0. So it's true. Like we expected. It should have done that. We can also easily find the space that, what is that actual space within that hump? Either the negative or the positive. We can do that just by changing the problem a little bit. All right. Instead of running it to 2 pi, let's run it to pi, because that will be the halfway point. So from 0 to pi of sine of x, this is all the same. It's still negative cosine x. We're just updating some of the terms here. So then this becomes pi instead of 2 pi. Now, negative cosine of pi is negative 1. So negative of a negative 1 is positive 1. Minus, and then cosine of 0 is 1, but that's negative in front of it. So that's negative 1 like that. That's 1 plus 1 is equal to 2. So the area underneath sine of x from 0 to pi has a space, has an area of 2. And that means from pi to 2 pi, that space must be negative 2. Because when we looked at all of them added together, it came out as 0. I think about other ones I can come up with to show you. This is as straightforward as it is. I'll do one more example. Do it right in Word. Let's change this problem to -1. No, let's do 2 to -1. Yeah, x cubed plus x. Okay, so we're going to do that problem. So what this problem without looking at a graph is saying that there's some function x cubed plus 2x, it looks like something. And we're finding the signed area underneath that curve from -1 to 2. That's what that's saying. We're going to assume geometrically we'd have no solution for that, so we're just going to use calculus, the antiderivative of that problem. And so the antiderivative, we just look at each individual part. Start with x to the third. Well, that had to be x to the fourth. And there had to be a 1/4 in front of it to account for the fact that there isn't a 1/4 in the original problem, right? It's just x cubed. When you take the derivative, right, 4 times 1/4 is 1, and then the x to the fourth becomes x to the third. That works. Now the 2x, it's even easier. That'd be x squared. Take the derivative of that, that's 2x. So we're going to, that's our antiderivative. We're going to change the design. There we go. And this will go from 2 to -1. Okay. This is equal to, use brackets and parentheses, help yourself out, get it all set up ahead of time, it'll be easier. All right, so now I need to work on the 2's first. So 1/4, 2 to the fourth, okay, plus 2 squared, that's on that side. And then minus, now I got to do the -1. So 1/4, -1 to the fourth, plus -1 squared. All right. Make my life a lot easier using all these parentheses. So on this side here, we get 2, 4, 8, 16. Divided by 4 is 4. Plus another 4 is 8. Minus. This is +1 fourth. This is +1. So 1 plus 1 fourth. So 5 fourths. So minus 5 fourths is equal to 32 over 4, 27 fourths. There we go. So that is the space underneath there. Notice how we dealt with having two terms here. Just using added parentheses will make this process not painful. But there are mistakes to be made that if you don't use parentheses, you're going to get sign errors and things aren't going to come out correctly. And the only other thing that actually no, that's the only things I want to mention today. On this next class, I'll mention some more details about this stuff, point out additional things. But this is the main concept I really want you to focus in on. Just getting used to the notation, what it means, what it's telling you to do, so we understand it geographically what it means as a signed area. We also understand how to, using calculus, take the antiderivative to solve this. And then this process and what this notation here means. We go from this to this, and then this is the actual action of calculating it, and then getting the final answer, which is just the signed area. And what signed area means. How this big space here has a signed area of 0, yet the smaller space of the same function has an area that's greater, because something here had to cancel out something else. So those are the general concepts that you need to take from this today. Any questions for me?
I have a question.
Yes.
How would I be able to calculate the values for the second derivative graph for the group project?
Calculate the values for the, what do you mean? Like what values are you talking about?
For the group project, how I need to find the values for the fetal and placental growth, how would I be able to find the values for the second derivative graph?
Do you take the second derivative and set it equal to 0?
Okay, so that's what I need to do?
Well, that's the one way. I mean, it depends. I know there's in one of the problems, I believe it says to, I don't know if it was for the group project or if this was for homework 5 to visually identify the location. But yeah, I mean, if you have the function, so you could go ahead and solve for the point of inflection.
Okay.
Okay.
Do we need values for like every point on the graph? Because we have the original function and we were able to just measure the values off of the original graph
Mm-hmm.
and then make a function off of that. But for the next one, we don't have a graph or a function. So like we could get like a point of inflection. We could get like, you know, things that are like more notable, like a 0 on the graph or something like that. But like I don't really know what we would do for the rest of the graph, like to actually get the shape of the graph and the actual values that would give that shape.
So you're talking about, because both sets of data they were both in that graph, right?
Yeah, but for the second derivative graph, for steps what was it, 5 and 6?
Okay.
So we're having trouble figuring out how to get a second derivative graph that matches with our first derivative graph.
So did you take the derivative? I mean, I'm not sure how it wouldn't match, right? I mean, if you have the first derivative equation and you correctly take the derivative of that. You should have a resulting graph. No,
Could you say that again?
you have right when you have a function that you're saying is the first derivative. You're calculating the second derivative of that, right?
Yeah.
So what else are you looking for from it?
So then we would just plug in points along that, like the same x values to get the f of x value.
No. You have the actual formula, the equation itself for the first derivative.
Yeah.
You find that. You find that from the data,
Uh-huh.
and that's what those variables are. The A, B, C, D stuff.
Yeah.
That defines an actual equation. Take the derivative of that equation that it creates.
Okay.
So you physically want to write out the equation itself and then calculate the derivative of it.
All right.
You
So
won't need data points at that point.
okay. So then when we have the derivative of that original function, the second derivative, then we would just plug in the x values into that second derivative function.
You said that really fast. Say that again.
Sorry. So once we have the second derivative function that we calculated from the first derivative function,
Mm-hmm.
we would just plug in the x values that we originally got into that, like the number of days.
It depends on what your objective is at that point. But yeah, you may want to take the second. You may want to do the second derivative test. You may want to check for a point of inflection. You see if something is an actual point of inflection. It depends on whatever your objective is with that data. But
Okay.
yeah, there's a couple of things that you could do. Yeah.
All right. I think
Okay?
I got it. Thank you.
All right. Anything else, guys or ladies?
Chocolate update.
We have not opened it up yet. That's where we're at with that.
I have a question.
Yes.
So if you have a graph that's displaying distance over time and
Hmm.
you find the integral, would it be like how far you went, like the area of distance, if you found an integral for that? I'm just trying to find ways where I can apply integrals.
I got you. Yeah. So if you're at a distance over time, the integral of that, your total distance. So we'll give you position over time. That would be, yeah. Your distance. I'm trying to think of an example in my head. If you went from 0 to 1, the total distance there is 1. Yeah, so if you're starting with the distance versus time, you want to go, that's like the top, that's like your position function. So it's like the top level. So you're not going to really take integrals on that. You would take the derivative and go downward. And so you could talk about the rate of speed that you were walking, a certain, through some path or something like that. And then you can take the integral of that, and that will give you the total distance that you were walking. That's the way you want to think about
Okay.
that
So
type of stuff. Yeah.
that be the displacement?
Yeah, exactly.
Okay.
Yep.
Now, if I had a graph that displayed acceleration over time, that would be velocity if I used an integral.
It would acceleration
Area.
is the acceleration is the derivative of the velocity,
Right.
right?
So therefore, if I take the antiderivative of acceleration, I go back to velocity.
Yeah, then you're doing the sum of your velocity. Yep.
Okay.
Displacement of that. Yep.
And so this is like a two-dimensional area we're talking about. So if I had like a double integral, it would be three-dimensional. It
Yeah.
would be like volume.
Yes.
Okay. And
Yeah.
so if I had three integrals, would that be like time?
Uh,
Because
uh,
it's the
that's
fourth
a good question.
dimension.
Would it be time? Huh. I mean, yeah, I think technically speaking, it would have to be. Yeah, there's a good point. Yeah, yeah, it could be. That's outside of my realm of knowledge, but it probably would be.
Okay. Thank you.
Yep, yep. Yeah, that's very good. Yeah, those double, to even think, yeah, I'm impressed that you even think that the double integral does exist, but yes, it does. That's good. Other questions? I've been looking at the timeline. The only thing we're gonna have one more homework that will focus on integrals, and then I think one more quiz, and then you have your group project and your final exam. So those things will come up probably both next week, both the homework and the quiz. It wouldn't be at the beginning of the week, but either the earliest the 29th, but it could be all the way up to that Friday, May 1st, where that stuff would be due. I don't want to bog you down with stuff, but I also want to make sure that you're just getting access to stuff before it just shows up on the final exam. And our final exam will be on the day that it should have been, as if we were meeting in person, which I believe is the 11th. I'll solidify that more and exactly what will go on, but we'll probably shoot for what our original time was, which was 5:30, something like that, unless we can all agree on 2:30, but I don't know. I'll work on that so that we get exact details on how we'll do this. Yeah, but that's all I have for you guys right now. If there's anything else, not free to go on, and I'll see you on Wednesday. There we go.
Have a nice day.
You too.